for joining us today for the webinar entitled Introduction to High Performance Computing using CUDA by Ms. Raazia Sosan, who has graciously joined us today. This webinar is brought to you by IEEE PF-KIET Student Branch. We are extremely delighted to have Ms. Raazia Sosan with us today. She is the Senior Lecturer in Computer Science Department at DHSUFA University. She received her Master's and Bachelor's from Hamdard University, Pakistan, and she is currently pursuing her PhD at DHSUFA University. Her area of interest is physically based volume rendering on the GPU. Thank you so much for being with us here today, ma'am. Before we begin, all our participants are requested to keep their mics and videos turned off during the entire session. If you have any questions, you can send them to the host with the chat with your name and affiliation at the end. Please be attentive during the session, as there will be a short and easy quiz at the end, which will be sent to you through email along with the recording of the webinar. You will have 24 hours to attempt the quiz in order to be eligible for the certificate. The certificates will also be emailed to you within 1 week from today onward. Now, without further ado, we'll hand over the control to our most esteemed speaker, Ms. Raazia. So, ma'am.
Bismillahirrahmanirrahim. Assalamu alaikum, all of you. Thank you, Fabiha, and your team for giving me this opportunity. As Fabiha has introduced, so let's start. In this webinar, you are going to learn about a few things. Basically, this is an introduction. So we are going to learn about what is high performance computing, what is CUDA, what are the prerequisites you need to have to learn this high performance computing and CUDA, why you should learn it, and what are the applications of high performance computing in using CUDA, and the role of high performance computing using CUDA in this COVID-19, and so on and so forth. We are going to discuss about the introduction to high performance computing using CUDA. There is a disclaimer before I move on that all the material that is shared in this course is based on educational material shared by NVIDIA under CUDA Teaching Center Award to DHSUFA University. So we are not allowed to redistribute this material. Okay, so my introduction, no need of it because Fabia has already introduced me well. So moving on to what is high performance computing. When we talk about high performance computing, it is something more than your conventional workstation that you use normally. In a normal CPU that you have a few cores, maybe 2, 4, 8, which are further divided into logical cores. If you have suppose 4 cores, then they will be logically divided into 8 cores. You can check this if you press Control Alt Delete and then you go to the taskbar and then task manager. There you can see that that how many cores are there. But when we talk about high performance computing, we are talking about a lot of power that is capable of solving large problems in any field. Basically, we are talking about not just 2, 4, or 8 cores. We are talking about thousands of core. So now we are going to dive into the world of parallel computing and using CUDA, and you are going to see that how the whole thing works. So basically, what is CUDA? CUDA is the full form of CUDA is Compute Unified Device Architecture. So what does this mean basically? What is Compute Unified Device Architecture means? In your conventional workstation, you just have a central processing unit. You have a single processor, that is your CPU. But when you talk about high performance computing, you have a heterogeneous computing environment. Now, what is a heterogeneous computing environment? You have 2 processing units. One is your central processing unit, which we are going to refer it as a host, and one is a graphic processing unit that is known as GPU. So when you introduce GPU into your workstation, this environment is referred as heterogeneous computing. So what CUDA provides us, it provides a unified device architecture. So we use the power of CPU and GPU. That is unification. And then we use the computation power of both the processing units, and we solve the problem. And this works this works in a very this is a very simple process. You just need to understand that how does it work. CUDA is basically an architecture for parallel computing on the GPU. Uh, this is basically meant for parallel computing on the graphic processing unit. It retains the performance, and it is based on C API, and it exposes GPU parallelism for general purpose computing. So it has a small set of extensions in C to enable heterogeneous computing, and its straightforward API to manage devices, memories, etc. And I have discussed what is basically heterogeneous computing. Heterogeneous computing refers to systems that have different kinds of processors, CPU and GPU, that interacts with each other to provide optimum performance. We are going to see this in a later slides, that how CPU takes control, how it delegate a task to GPU, how GPU performs a task and give back the control to CPU. This whole cycle we are going to see today. A very brief introduction to this whole process, and let's move on. That what are the prerequisite for this whole thing, that for CUDA what you should know. Basically you just need to have a little experience with C or C++. That's it. And ideally, really, this is the truth, that you should only know how to use a C compiler to compile a basic hello world program. Means you should know that we have a main program, right? And we can just print a hello world, but that's it. That's all you need. You don't need any GPU experience, you don't need any parallel programming experience. And since we are talking about graphic processing unit, no, you don't need to have a graphic programming experience. So what we are going to build up all the concepts. Keeping in mind this is a very introductory session, but still we are going to build all the concepts based on a simple hello world program written in a C language. So why you should learn it? It basically a simple and easy it is a very simple and easy to use GPU programming API based on C language. Before I introduce what is GPU programming, initially graphic processing unit GPU was introduced for only graphics, for rendering, for games. But then it was realized that the power of GPUs, the power of thousands of cores, can be utilized for general purpose computing like AI, machine learning. In bioinformatics, we are going to see the areas in a later slide. And so therefore the term was introduced, general purpose GPU programming. So now we use GPUs for everything. If you talk about AI, machine learning, deep learning, even in visualization and in bioinformatics, and a lot more. There is a lot more now. In even in autonomous systems we are using it, right? Moreover, a specialized toolkit is provided by NVIDIA, which includes everything: sample cores, debugger. It's very easy to learn basically, and NVIDIA gives us a lot of learning material, which makes it more easy for all of us and for all the beginners to get started on with this, right? It is a very it has very helpful online forums. It can be applied in diverse areas, right? And it is something that was not possible in the early days, and it was only possible through cluster or supercomputers. But now we can do complex we can solve complex problem or a large problems using high performance computing using CUDA. So CUDA application domains are as follows. We can use them in bioinformatics, computational chemistry, computational finance, fluid dynamics, computational structural mechanics, data science, defense, electronic design automation, imaging and computer vision. And not limited to that, but machine learning, medical imaging, numerical analytics, and weather and climate. We are these are the and there are much more. There are still much more, like we are facing this COVID, and still um, we are using NVIDIA is participating and playing its part in this situation also. We are going to see it again. Case studies, CUDA case studies are that we can use them. These are a few case studies. It is used in medical imaging, bioinformatics, supercomputing centers, and then we have seismic exploration, GIS, defense, filmmaking and animation, computational finance, computational fluid dynamics, and CAD/CAM images, right? So now we will move on to the role of HPC using CUDA in COVID-19. This you can see this slide in detail. This is taken from NVIDIA GTC 2020 keynote, in which the CEO Jensen Huang introduces data center scale accelerated computing, and he shared that NVIDIA and played its part in COVID-19. HPC, high performance computing using CUDA, has been involved in number. First, we see that in sequencing of virus genome in just 7 days, and not at all possible using a conventional desktop machine, but it is only possible by using high performance computing using CUDA. More on, moreover, we can real-time infection rate analysis is done by Plotly NVIDIA, and um, and then we have scripts screens 1 billion drug compound in 1 day versus 1 year. Now this is something really huge, that CUDA and NVIDIA hardware, and then it just took 1 day. And then in moving on, we have first 3D structure of virus spike protein, and that was also possible by high performance computing using CUDA. And then AI based COVID-19 classification of different scans of lungs. That is also a contribution done by NVIDIA using high performance computing using CUDA. And then we have I shared earlier that it is not only based on, it is not limited to now deep learning or AI or anything. Now we have moved on to autonomous system like robots. And then this is the next thing here. We can see that robot medical delivery supply. This is a Kiwi bot named as Kiwi bot, and this is made for medical supply delivery. And then we have AI elevated body temperature screening system, and which screens the temperature of the body's life. So this is a whole this whole possibilities. These all are possible by using high performance computing using CUDA, and there is much more where we can use this platform. So moving on, so now here from here the introduction starts. The basic term that you should be aware of is heterogeneous computing. In heterogeneous computing, there are two kind of processor, as I just shared, that you have a host, that is your CPU, and then you have a device, that is your GPU. And then if you remember a basic C program, it only have a C program, basic C program. It says that you have a main, and then you write int main, and the parameters are void, and then you have printf hello world. That's your main, right? And then if you want to add a function, you can add a function and then you call it from main, and the control goes, when the function is called, the control from main is passed to that function, and then the function execute and comes back to main. This is the whole process that we know, that a basic hello world program in main using C language. How does it work? We know that the control is first given to the main function, right? Next, we have a term kernel. It is a simple function. Simple function. You write a function that runs on host, that is your CPU, but you write a function that runs on GPU, that is known as kernel, right? A special function that is run on the device, but it is called from the host. We should keep one thing in mind, that whenever we are writing a program, a parallel program, uh, that is meant for a heterogeneous computing environment, that is meant to be using CUDA, um, it the control, when you compile your code, when you execute it, the control is first given to the host. Host is your central processing unit, right? That is the host. And then it is going to compute, it is going to process the host part, and whenever there is a kernel function call, from there the control is being delegated to the kernel function, right? We are going to see a program, and then this whole thing is gonna make sense for you all. But for the time being, we are just introducing the terminologies. And kernel is a special function basically that is run on the device, but it is called from the host. Called from the host means that the controlling power is the host, that is your CPU, right? Any data that is required for processing is passed as a parameter to the kernel function, much like normal function in C. You might have noted that in C we write functions and we write pass parameters, right? So in GPU, if you have to pass some data, so we write functions that, and the data is passed as a parameter. That's it. And kernel function call is asynchronous. For the time being, just remember this point, and in the later slide I'm going to elaborate in much detail that what does this mean. Kernel function call is asynchronous. There is a whole lot of explanation for this particular sentence, that a kernel function call is asynchronous. Moving on, we have another thing that says execution configuration. Now if you just skip uh, if you just for a moment, just if you can skip these angle bracket thing, and if you see just my kernel and bracket, these brackets, so it is similar to a normal function call which we have been doing in C language, right? When you call a normal function in your C language or a C++ language, we just write a function name, then open bracket, close bracket, and if there are parameters, they are given within the bracket, right? That is your function call. When we call a kernel function, when we are calling a kernel function, this is introduced: three angle brackets opening, three angle bracket closing, and then in between there is a number. What is that number? We are going to see in detail later. This is known as these angle brackets, and this is known as kernel execution configuration or kernel configuration, right? um, when a kernel function is called from the host, it must provide the number of blocks and number of thread in each block. The number we are saying here, 32 comma 32, the first number indicates the number of blocks. What are number of blocks? We are going to discuss, don't worry, just this is just um, the term I am introducing here, execution configuration, right? Execution configuration is this thing, these angle brackets. This thing is known as execution configuration, right? And the second parameter is threads per block, right? And we are going to divide the workload, and this and organize them in terms of threads, and this is given in the execution configuration. For the time being, I am not expecting that you are going to understand that what I just said, but that's okay. You should just know what is execution configuration, something written in these angle brackets, right? So this is basically a difference visually. If you see a function, a normal function and a kernel function call, so you can clearly identify that something written like this having these angle bracket is a kernel function call. Something just written like my kernel opening bracket closing bracket, nothing in between, is a normal function call that is going to be executed, run from the host, execute on the host. That's it. But a kernel function is called from the host but executed on a GPU, right? So the big picture, what is the big picture? Big pictures tell us that how the whole program flow takes place. It is going to start on CPU. CPU takes control. Control is given to the main program. Main program executes the host part. Instruction one by one are executed. As soon as you get a kernel call function, the control is delegated to the GPU. GPU performs its part, but you are not going to stop there. The CPU is going to perform its part, right? Now there are two things going in parallel: GPU is performing its task and CPU is performing its part, and then the code is going to end as soon as the CPU finishes its part. right? Again, I'm going to repeat it with the example in the coming slides. If you are skipping things or you're not getting it, it's perfectly fine, and this is completely normal, so no need to worry about it. So how do we identify a kernel function? Basically, a kernel function is callable from host. As we said, it is callable from host but executed on the GPU. We have a qualifier. This is basically 2 underscore. Global is the keyword and 2 underscore. This specifier is added before a function, and that function is basically a kernel function. I'm skipping this point for a moment, and then I'll introduce. Just let me show you a kernel function. This is a kernel function. If you can see that we have written a normal function. If you don't have this global specifier here, this is just a normal function. When you add this, there are double underscores, global double underscore. Now this is a kernel function. You have written a main, right? And this my kernel, and this is a kernel call, right? If there were no kernel configuration, it was a normal function call. So this is a example of how your basic code looks like. I had to skip to this slide just to make you give you an idea that what we are talking about. So let's move back, and then let's start again. So the big picture tells us that the code that the control is a control will be starting from here integer main, and then it is going to come here on my kernel, and here GPU comes in action. This function is going to be executed, and in the meantime CPU will keep on executing till it finishes, right? So how do we write the code? For that we need to have some setup. If you have a GPU enabled laptop or a desktop machine, that's perfectly fine. You can just download the latest GPU and computing SDK from the website, and then you may have two options. Basically, you can use a command prompt and write your code in notepad and save it as .cu file, and otherwise you can use Visual Studio IDE. In If you use command prompt, then to compile it, first of all you must have NVCC in the path, and you should open and execute in Visual Studio command prompt, right? So just like you do G++ compiler, you write it notepad file, and you used to do this for C language, right? Similar process for this NVIDIA code. You CUDA code, you can write NVCC, and we write the file name, and we can provide -o flag, -o flag, just to provide the output name for the executable file, right? And other way you can do is that using a Visual Studio IDE, and you just need to go new project, search for CUDA, and then just add the file, right? You're directly going to create a CU file for you, right? And suppose you don't have a GPU based laptop and you don't have a GPU based workstation, then also it is completely fine, because we have Google Colabs, right? So this link will help you in setting up a Google Colab using they provide Google Colab provide you two options, either Python or C. So this tutorial here given on this link is going to enable C for you, and you can write your code in C, right? So Colab is a very powerful platform here nowadays, and it helps it removes the binding and the barrier of having a GPU based laptop or a machine, and you can directly write everything in just your web browser. So this is a very convenient way of doing parallel programming. Okay, so now we are going to see a basic hello world on host. So what I was trying to tell you, a basic C program looks like this. You can write main, and then you write printf hello world and return 0, right? And you have and you can save this, write this code in notepad and save it as hello1.cu. That's fine. And then you are going to write this, you are going to open up Visual Studio command prompt. You are going to write nvcc hello3.cu, whatever your file name is. And even if you don't provide this flag, that's fine, just press enter. the NVCC compiler is based on C, right? So whatever the C part, it is given to the C compiler, and whenever the GPU parts come in action, it is given to the NVCC compiler, right? So what happens is standard C that runs on host. This is something I was trying to tell, that NVCC hello1.cu, and we did not provide the -o flag, that's fine, and then a file is going to be generated, that is a.out. Just run it and you can see a hello world, right? NVIDIA compiler can also be used to compile program with no device code at all. The reason is that CUDA is built upon C compiler. That is why this is possible. So this just should not be the norm. This is just for a basic example that we are writing a code with .cu extension, that is CUDA code, and we are just writing it with just the no device code at all. This is just an example, right? So next, we are going to introduce a hello world with the device code. So now you have introduced a kernel function. How I can say that this is a kernel function? I can say this is a kernel function because of this global specifier, right? This global specifier tells me that this is a kernel function. Now kernel function is called from host and then executed on GPU, right? So just stick to the basics. Basics tells us what we have covered till now, that heterogeneous computing, a computing environment that is involving two or more computing units, that is host and device. And number two, we are having a kernel function. Kernel function is executed on GPU, but it is called from host. How do we write a kernel function? Write a simple function, and then the code in the function, definitely it is going to be subjected to your parallel programming, and the way you organize your data and all. But you have to mention the global specifier before a function to make it a kernel function, right? And then we have kernel configuration. Whenever we need to call a function, we just write a function name and opening bracket, parameter, closing bracket. But when you are calling a device function, you have to give this execution configuration, which is written in a format: three opening angle brackets open and three angle bracket close, and then in between you have to provide a number, that is number of block and number of thread, right? And then we have a simple printf hello world, and that's it. So what is going to happen, that when you are going to execute this code, the control is going to go on directly on int main, and then the next line my kernel. Here the GPU will come in action. Now GPU is performing a task, but CPU does not stop here. CPU does not stop and wait for GPU to finish. Instead, it continues to the next line, printf return 0, and there is a chance that GPU did not finished its work, finished the execution, but CPU finished and the code ends, right? So I would like to map this whole thing now. We talked about number of blocks and number of threads, execution configuration, a computing environment. Now let me map it to a real world example, a real world scenario basically. A very simple example that is going to make it maybe easier for you to understand that what this whole computing environment look like. Imagine a classroom, all of you. First of all, imagine a classroom, and there is a stage where the teacher comes and gives lecture, right? And then there is a whole classroom, right? So we all are ready with the imagination that we have a classroom, and in classroom we have a teacher portion, and then we have a student portion, right? So let me say that the student portion is the GPU and the teacher portion is the host. So the classroom is now a heterogeneous computing environment. Now, if I talk about a teacher, maybe you can consider it as a less number of cores. The teacher is a single unit, so maybe there is one core only. But if you talk about student, there is a whole class maybe of 50 students. So can you compare the number of core if you talk about host and GPU? There is one place where there is only one person working, but there is another place where there are 50% working, right? So map it on CPU and GPU. CPU, I just shared that you have 4 cores, maybe 8 cores. But when you talk about GPU, it's not a number within 1 to 10. It is a number in thousands, maybe 3,000, maybe 2,000, right? So the number of workers you are having, is a lot, right? So I hope this makes sense now, right? Acha, then next I talk about what type of a work I'm gonna give to for a parallel programming. What type of a problem? Suppose that we have a very huge array. You are, as a person, just think that we are given a huge array, maybe of 1,000 element, and we have to square the whole array. A single person doing it, assume. Gonna do it for first element, second element, third element, so on and so forth. You are going to repeat the task 1,000 times, right? That is going to take a lot of time. But when you do the same task on GPU was your classroom. If a single teacher is even doing 1,000 squares, is going to take a lot of time. But if she gives this task to her class, a class of 50 students maybe, so the thing is, instruction, there was a single instruction, that is to square the number, right? But if this task is given to a student, to a class of students, that is a 50 or 60 or maybe 100 or whatever number, the task is going to be divided, and then every student is going to perform maybe 3 or 4 calculation, right? And then the task is going to end sooner and in a more better way. If a teacher is going to take a whole day, maybe that class is going to solve it within a few minutes. This is your heterogeneous computing environment. This is how your parallel code works. I hope I'm clear with this example, and I hope that this makes sense. Now, if we talk about this int main, the code, the control is given to the host. So the host is the teacher. Whoever enters in the classroom from the door, the first person, the controlling authority there is a teacher. Teacher is gonna take the problem, and then teacher is gonna delegate the problem towards the students. So whatever the problem is, if you map it back to the parallel computing environment, whatever the problem is, it is given starting from int main, and then from main, the power from the host, it is delegated to the GPU. GPU performs the task, and that's it, right? Acha, if we move on, and I say that in the class of 50 students, let's make 10 groups, 5 students each, right? We make 10 groups of students, and we have 5 students each. Number of students remains 50, right? So those 10 students are your number of blocks, and the 5 students within each group is your number of threads within the block, right? So the first parameter here in the my kernel, that is like in this execution configuration, the first parameters we tell number of blocks, and in the second parameter we tell number of threads per block, right? You had a let's revisit this. You had a grid of 50 students which were arranged in 10 groups having 5 students each. So we had a grid of 50 threads which was organized as 10 blocks having 5 threads each, right? So basically, execution configuration defines that how do you distribute the task, how do you group your threads, and how do you divide the workload. And similarly, resources are also divided. Resources are divided thread-wise, resources are divided block-wise. So this plays a very critical role here. You need to be very careful. Initially, it's hit and trial situation while you are selecting your kernel configuration. It is a hit and trial situation initially, but that's fine. Eventually, you learn that what is the perfect kernel configuration you need to provide to get the maximum computation power and minimum time and maximum computing. uh, you will eventually learn it. Initially it's hit and trial, right? So I hope that the whole scenario is clear, and then let's move on. So what we did was same. You write NVCC. We are assuming that we are compiling this code using Visual Studio command prompt, and we are writing a simple. Just copy this text in a notepad file, save it as hello2.cu, and be ready that you should have NVIDIA SDK installed. Whatever the latest version is, just install it. Or if not like this, there is no point in doing this all. Just type this code in Colab. First of all, set up your Colab, given the link. Previously I just shared the link. Just set up the code, and then just type this code in the Colab, execute it. That's it. So what we are doing here, hello world is just be the output. What we are doing here, we say that one block and one thread. It means that there is a single student in the class, right? How are you going to, just like I said, 10 comma 5, 10 groups, 5 students, 10 into 5, 50 students, right? So 1 into 1 tells you that there is one thread only. And what does this mean? That if you map it on the classroom scenario, you are going to say that there is only one student in the class, right? This is just a basic example. That is why we are just using one thread, right? So the scenario is that you have a 50 students class, and all of them are going to perform a single instruction, which means that whatever code is written in this kernel function, that is the instruction. What is the instruction? This kernel function. Here I am going to give the square code, and this whole function is known as an instruction that is going to be executed on each thread, right? I hope this makes sense. Even if it doesn't, that is okay, and this is completely normal. as uh, as soon as we are going to move forward and then come back again and then move forward, and this way you are going to understand how the whole thing work, right? Next we have two new syntactic elements. First was this global specifier, which I have been highlighting again and again, that we need to have this global specifier that makes a normal function a kernel function, that identifies or makes this as a kernel function. And next we have CUDA C++ keyword global indicates a function that runs on a device and is called from a host. There is another specifier now I would like to tell you here, which I skipped here. This is a device specifier. You can write a function, right, that is also a device function, but it is called from device and executed on device. For example, a GPU calls another function on GPU, right? So that that is a that in detail we are going to go later, but just to give you an idea that there can be a device function. By making a function and adding this specifier underscore device underscore, you can make a device function that is going to be executed on device, and it is going to be called from device. For example, a kernel function calls another function, that function is going to be a device function, right? So next, back to the syntactic elements. So this was one global specifier. So what happened was that NVCC separates the source code into host and device component. You can see it here. This is the host component and this is a device component, this function. And then device function processed by NVIDIA compiler, and the host function is processed by standard host compiler, that is your G++ and whatever, right? The next thing is my kernel and this execution configuration. Triple angle brackets mark a call from host code to device code. It is also known as a kernel launch. And parameters, what we use were one by one, that is, we just launched a single thread. What does this mean? Like, you have a class of 50 students, but you don't want to use the whole of the 50 students. Maybe you are going to launch um, two groups, 5 students each. So you're going to write angle bracket 2 comma 5. So only 10 students are going to be active solving some problem. Similarly, you are going to launch only 10 threads, right? So this is how many number of threads you need to work on the data. Now we are talking about the massive data. Basically, for parallel programming and there is a single instruction and a massive amount of data, right? You just saw that the example I gave, that you have 1,000 elements which you need to square, and the single instruction is square, and the data set is a huge, right? Which cannot be done via conventional computer. The conventional computing environment cannot solve this, right? This is all that is required to execute a function on GPU. So this is our hello world code, and we executed it. And this is something, right now my kernel function is not gonna do anything. It's just empty. It's just for a brief introductory example. Now in the next example, what we see is that now we have added a simple printf statement that says hello from GPU. Okay, now first of all, this is not recommended that you use printf or any such statements, but for example, and for just an example and learning purposes, we are using this. So now how does your code look like? Just have a look. This is your kernel function, in which we have just a single statement. The instruction just prints a hello message, hello from GPU message. If you see your host code, here we have a simple printf statement, right? um, Hello from the CPU, and then you have a kernel function call. How is this kernel function call? How are we saying it? We have this kernel configuration here, right? And in addition, we are saying one block and 32 threads. Means that if you map it again to a real world example or scenario I just shared, that there is a one group having 32 students there, right? One block, 32 threads, right? And then you have printf hello from CPU after kernel execution. Have this code, right? So it means that if you have a class, map this scenario on again the classroom scenario. You have a class of whatever number of students, maybe 50, but then you are launching, or you are using only 32 students out of them, and you make a single group, and then each or each of the student of that group, like 32 students and one group, these are active right now. The rest of the 18 students are not active. They are not doing anything. We selected 32 students, put them in one group, and now they are going to execute this hello kernel function, which means each of them is going to print hello from GPU, right? Wherever, on a paper, on a screen, wherever, they are going to print hello from GPU, which means that this instruction is going to be executed 32 times. I hope this makes sense to you, because 32, 1 comma 32 is 32. 32 threads are active right now. 32 threads are gonna execute this function void hello kernel. Therefore, this instruction is going to be executed 32 times, right? So let's see what happens. So what happens is, this is a serial code, and this is a parallel code, of course, and then this is a parallel kernel function, right? And this is again a serial code. The control is going to be, the control will start from main. A printf statement will be executed. On screen you are going to see hello from CPU, and then you are going to have hello kernel, means kernel call is there. From here GPU becomes active, and then the control of CPU does not stop and does not wait for the GPU to finish the task, and it is going to print hello from CPU and then return 0, and the code ends. I am saying something which should be alarming for you, that why CPU is not waiting for the GPU to finish the task. Let's discuss this in the in the later slides. So this code is going to be executed on CPU. This will be executed on GPU, and see the output. The main thing is just see the output. Hello from GPU before kernel execution, hello from GPU after kernel execution, and then you have a few hellos from the GPU, and then the code ends, right? So what is happening is that, as I said that CPU comes in action, control goes to main, hello from CPU, and then GPU becomes active. There is something that you should know, that for the first time you execute a code on GPU, there is a warm up time. So there, whenever we are going to execute a code for where we are targeting performance, so what we are supposed to do, that we are going to execute it 1 2 3 4 multiple times, and then when your hardware is completely warmed up, then we are going to take that note that particular time, right? So what happens is that maybe here the GPU was not warmed up, and it took some time to start the execution. In the meantime, the CPU did not wait for the GPU, and it moved on to the next instruction, printf hello from CPU. We have this on the screen. And then when the control was going towards return 0, at that time GPU got some time, and it prints a few hello world instructions. And without waiting for GPU to finish the task, the host ended the program. This happened. Now this whole scenario is known as asynchronous call. I said earlier that note this line, that a kernel function call is asynchronous. This is asynchronous. This particular thing where you're not waiting for the GPU to finish the task and you are moving on with the rest of the host code, this is asynchronous, and this is not the desired behavior. Map it to the classroom scenario, in which you have a teacher, and teacher there was a computing problem. Host is your teacher. She took the problem and delegated it towards the class, like 10 groups of students having 5 students each, and we are using 50 students. What happened, that students are doing the task and the teacher left. Without waiting for the results, the teacher left. This is asynchronous. So what then, this is an undesired behavior. What was needed was that the CPU should wait here. After the kernel call, CPU should wait and let GPU finish the task, and then CPU should proceed with the rest of the statements. So we need to make the asynchronous kernel call synchronous. How can we do that? Let's see in the next slide. Here, things to be noted are just what I said, that CPU execute first and then invoke GPU code asynchronously. Here, just I discussed that it started with main printf, and then GPU was called, and it was invoked, and it was an asynchronous call. Therefore, what happened? The CPU execution continues to the next statement immediately after the kernel launch, right? It never waited for the GPU to finish the task. What we want is that we want that CPU execution to wait for the GPU to finish and then continues its execution. So we need to add a function here that is known as CUDA device synchronized function after the kernel launch. This function is gonna be enforce a synchronous function kernel function call, and this function is going to force CPU to wait for the GPU execution to finish. Right? So here, after hello kernel, right? After hello kernel, you are going to write CUDA device synchronize with opening and closing bracket, and this function is going to enforce CPU to wait for GPU to finish the task, like this. CUDA device synchronize. I'm going to add this after the kernel. Okay, we have added this after the kernel, and then now what happens is int main control is here. Then we are going to start with printf. So the first line will be hello from CPU. Then the GPU is invoked. Control is given to the the GPU is invoked here. So we go to this function, kernel function, and then we have a few printf statements. Now the GPUs for this on GPU, we are going to launch one block of 32 threads. Each of the thread is going to execute this function, which means that you are going to have 32 statements: hello from GPU, hello from GPU, hello from GPU. We have written CUDA device synchronize, because of which the host is going to stop and wait here till the GPU has finished the task, and then we are going, then once the control is returned, then the host is going to continue. Then we are going to have a printf hello from CPU after kernel execution, and then we have return 0, and then the code is going to end. It is a best practice that we write integer main, and since the return type here is integer, therefore we are going to write here return 0. Return 0 means that execution was successful, right? So since the return, if your return type is void here, definitely there is no need of writing a return 0 here, right? So moving on to the output, here is the output here. First of all, hello from CPU, then GPU is invoked, 32 hellos from GPU, and then hello from CPU after kernel execution. And this is what that was desired actually. This is your desired output. So if you map this whole thing on a classroom scenario, the teacher said hello from CPU, and then one group was made of 32 students. Each had that function. Every student wrote hello from GPU, right? There are 32 students, so we have 32 times this statement. And then once the code ended, the teacher concluded hello from CPU after the kernel execution, and then the whole problem was solved. For example, just an example, right? So moving on to next, basically there are this is a this was a basic example to give you all an idea or an overview of how a heterogeneous computing environment work, the coordination of a CPU and GPU, how a parallel code is written. A basic parallel code is written, the role of threads and their organization in form of block, right? And this is just an overview. Again, I'm again repeating, this is an overview. There are more things there, and they're very easy to understand. If you get a grip of basics, then it's very easy to understand what's going on in this heterogeneous computing environment. There are 5 steps when you write a program. First of all, what we need to do here in this code, there was no memory allocation part because we are just dealing with the printf statements. But if you are dealing with a problem, suppose squaring of a number, a squaring of a large array, or maybe adding 2 arrays, or maybe adding multiplication of 2 arrays, or whatever, these are again simple examples. We have to deal with much more complex examples when we talk about rendering, when we talk about machine learning, bioinformatics. So we have to deal with a lot of different complex instruction, and then it's not as simple as just adding 2 vectors. It's not as simple as that. So but this involves allocation of GPU memories. Look, allocation of GPU memories means that there are 2 different processing units having their own architecture. So you have your own stuff, so you can't just use it on your own computing environment processing unit. You have to allocate GPU memories on GPU first, then you are going to copy your data from CPU to GPU, which means, and then you are going to invoke the kernel, and then the result is going to be computed on kernel, and then it is copied back from GPU to CPU, and then we are going to deallocate the GPU memories. So in this hello world, we just talked about how we invoke a CUDA kernel. That was the main part. So we just talked about that. If we have a few more session later on sometime, or a workshop or whatever, so in that I can elaborate in detail how this whole program is written with these all 5 main steps, right? So for the time being, considering that we had only a limited time for this webinar, I just talked about how we write a basic code and involved CPU and GPU and gave you an idea of heterogeneous computing. Following are some references for you all. These are some books and then blog. You can head to CUDA zone. Then there are educational resources, there are webinars, and again there is a lot of learning material waiting for you guys, so that you can learn from it, right? So lots of things are free here, so there is no need of paid session or anything, right? So next, next I'm going to tell you about CUDA at DSU. Our university was awarded, it was awarded CUDA Teacher Center. It won actually CUDA Teacher Center Award, in which we were awarded 5 hardwares dedicated, and we made a dedicated CUDA research lab for high performance computing research using CUDA, and a few of research areas that are currently active at DSU are computer graphics and visualization. That's my area. And then we have machine learning, deep learning, and bioinformatics. And that's my email address. If there are any questions you want to know, if there is anything I can help you with, feel free to write me on the given email address. And before I take the question answer session, I would like to thank a few people here. First of all, thanks to PF-KIET IEEE Student Branch, Fabiha and her team for providing me this opportunity. I am thankful to my university, DHA Sufa University, um, f- uh, because of which I am being known. And then I'm thankful to NVIDIA, and I am thankful to my mentor, Dr. Mohammad Mubin Muania. Because of him, I'm here, and he taught me all of this. And I am now capable of giving this information and giving this learning to you all. So I'm really thankful to my mentor. So now I'm done with the webinar, and I would like to answer questions, whatever questions are there.
Thank you very much, ma'am. Host, do we have any questions in the chat so far?
Yes, I can see some.
Okay, yes. Let us look forward to answering them.
Okay, then. There is a question from Mohammad Ashad. What is the purpose of writing return 0? I explained already, right? I hope, Ashad, it's clear. Since you're writing integer main, right? So the data return type of main was integer. That is why I was returning 0. The best practice is that a well formatted code, and the way it is accepted everywhere, is that you should not write void main void, you should write integer main, so you can return an error state, right? Achi ji. Next question we have from Hasnan Chaudhary. Ma'am, kindly tell the work of kernel and what is the difference between CPU and GPU. Kernel, you have consider, first of all, to answer this, I would like to say that first of all, consider that you have a simple CPU code जो आप लिखते आए हैं, that is int main, sorry void main void लिखा होगा आपने, और उसमें आप printf की simple एक statement लिखते हो और आप एक sum का function बनाते हो और main में उस sum के function को call कर लेते हो, right? This is your simple program. But अब क्या होता है, ये पूरा कोड जो आपने लिखा है ये simply आपके CPU पे execute हो रहा है. This is just CPU, but you need to have a specialized function that is going to be executed on GPU, right? So for GPU, you have to make your function a kernel function. That is a kernel function that executes on GPU, right? Miss Fabiha, I can hear a lot of echo. Some mic is on, please mute it. And then we have, that is a kernel code, right? That is a kernel function. Now a normal function, if you add a normal function, I'm just saying it in terms of appearance, the code written in that function is have to be a parallel code. You just write a device specifier and global specifier before a function, and that indicates that this function is a kernel function. A difference between CPU and GPU, a very good question. A CPU is your normal machine, normal processing unit, and GPU is a graphic processing unit. Basic, in simple language, I can tell you, both of them, of course, have a very major difference in their architecture. But in simple terms, if CPU have 8 cores, GPU have 1000 cores, right? So it means that you consider it as you have 8 people to do a work and you have 1000 of people to do a work. So their performance capacity, their working capacity, that matters a lot. That is a very big difference. So when we are talking about massive data sets, what we do in data science, what we do in machine learning, what we do in AI, what we do in deep learning, rendering, complex computing, and we have a large integral to solve. So they are not so easily doable on conventional CPU, because your machine is gonna hang. In simple, if you just see a basic difference, try executing such problem on a CPU, it's gonna hang a lot. And then if you do it on GPU, if you define a GPU, it has a number of cores, so it means that it is gonna perform a lot way faster, right? um right. So how we check whether CUDA speed up my execution? Of course, if you see, if you are talking about see, first of all, if I go back to the if you see the initial slides where I told you that where this CUDA is being used, that is a big picture and a big application of CUDA, right? So the application of CUDA is not just adding of two vectors. It's like you are killing an ant with a rocket, right? So this is not the real example, right? So what we are doing here is we are dealing with application areas. इसके क्या application areas है? हमारे पास बहुत सारा data set है, उसमें से हमने मशीन को ट्रेन कराना है और उससे हमने नेक्स्ट टाइम हम उससे कुछ क्लासीफाई कराएंगे या प्रिडिक्ट करवाएंगे. तो इट मीन्स दैट एक नॉर्मल मशीन को आप अगर ह्यूमन लाइक इंटेलिजेंस दे रहे हो, जिसको हम एआई कहते हैं, तो उसको आप बहुत सारी एग्जांपल दिखाओगे ना, बहुत सारी एग्जांपल, ठीक है? तो बहुत सारी एग्जांपल है, ठीक है? तो वो बहुत सारी एग्जांपल एक नॉर्मल सीपीयू आपका नहीं कर सकता. वो किस तरह करेगा? आप बताओ ना. एक आपके पास एक बिल्डिंग बनानी है, उसमें आपके पास सिर्फ 4 लोग हैं, और आपके पास जो है 4 लोग हैं, और दूसरा हमारे पास एक बिल्डिंग बनाने के लिए मतलब कोई 100 लोग हैं, तो ऑफ कोर्स 100 लोग जल्दी काम कर लेंगे, राइट? राइट. यू हैव अ हैवी ड्यूटी कोर्स. सीपीयू के कोर्स में हम कह दें कि बहुत ताकतवर 4 लोग खड़े हुए हैं, अगर आपके पास 100 नॉर्मल लोग हैं, तो वो अगेन 100 नॉर्मल लोग ज्यादा बेहतर काम करेंगे. दिस इज अ मेजर डिफरेंस बिटवीन सीपीयू एंड जीपीयू, दैट यू हैव अ लॉट ऑफ कंप्यूटिंग पावर. कंप्यूटिंग पावर का मतलब है जितने ज्यादा कोर हैं, हम उतने ज्यादा इंस्ट्रक्शंस पैरेलल में चला सकते हैं, right? If I am telling you about that I have a 1000 array, 1000 element array, तो वो एट अ टाइम सीपीयू में 4 कोर में कैसे डिवाइड होगा? बट अगर उसी के बजाय हमारे पास वो हम 1000 ऑफ कोर वाली मशीन पे चलाएं, जैसे जो हमारा जीपीयू है उस पे चलाएं जिसमें थाउजेंड्स ऑफ कोर होते हैं, तो वो जल्दी चलेगा, क्योंकि हर बंदा एक एक काम कर रहा है ना, ठीक है? अच्छा, अब एक और सवाल आया है कि जो सीपीयू आप कह रहे थे, जो CUDA स्पीड अप माय एग्जीक्यूशन कैसे पता चल रहा है? ऑफ कोर्स जब आप इनको CUDA को एप्लीकेशन एरिया में लेके जाते हो, जब यू टॉक अबाउट रेंडरिंग, व्हेन यू टॉक अबाउट एआई, डेटा साइंस, मशीन लर्निंग, डीप लर्निंग, उसका कोई प्रॉब्लम आप सॉल्व कर रहे हो, देन यू सी CUDA इन एक्शन. देन दैट इज, अगर आप उसको बिना CUDA के करोगे तो आप नहीं कर पाओगे, डेफिनेटली यू वोंट बी एबल टू सॉल्व इट, राइट? अच्छा जी, अब नेक्स्ट क्वेश्चन लेते हैं. Next question says that when we are doing the thread and block, who is responsible in a class example of assigning groups and its member? Very good question. The load is on CPU or in GPU? No, this organization is done by GPU. Once CPU का काम क्या होता है? This is a very very good question. I must appreciate. It means that something कुछ ना कुछ समझा है आपने. CPU का काम क्या होगा कि उसने सिर्फ GPU को टास्क दे दिया कि ये टास्क करना है. अब जीपीयू के पास अपना मैकेनिज्म होता है विच एक्चुअली ऑर्गेनाइज. हमारे पास सीपीयू से क्या गई थी? कर्नल कॉन्फ़िगरेशन गई थी कि हमें इतने थ्रेड्स एक्टिव चाहिए इतने ब्लॉक्स में. तो व्हाट हैपेंस इज कि जीपीयू में अपना मैकेनिज्म होगा, कंसीडर इट एज अ मॉनिटर ऑफ द क्लास और अ सीआर ऑफ अ क्लास, जो कि ग्रुप्स बना के थ्रेड्स को एक्टिव कर देगा. आई होप दिस क्लियर्स योर क्वेश्चन. अच्छा जी, how after dividing of blocks and reuniting of block works? अच्छा जी, अब एक चीज ये है यहाँ पर जो मैंने बतानी थी कि कर्नल फंक्शन जो है ना, उसकी कोई रिटर्न टाइप जो होती है वो हमेशा वॉइड होती है। कर्नल फंक्शन जो है वो हमेशा रिटर्न टाइप क्या होगी, वॉइड होगी। इट इज नेवर एवर गोना रिटर्न एनीथिंग। इसका रीजन ये है कि अगर 1000 कर्नल या 1000 स्टूडेंट्स एक्टिव हैं, अगर सब रिटर्न करना शुरू करेंगे तो रिसीविंग एंड पे सिर्फ एक होस्ट बैठा हुआ है, वो कैसे रिसीव करेगा? दैट्स नॉट पॉसिबल, दैट्स नॉट एट ऑल पॉसिबल। अ डिसेंट वे ऑफ डूइंग इट इज कि जो रिजल्ट हमें स्टोर कराना होता है ना, उसको हम एज एन एरे, उस एरे को हम पास करते हैं और रिजल्टेंट एरे, सपोज वी हैव टू यू राइट अ सिंपल कोड ऑन C++ और C which adds two arrays। तो आप उसको दो पैरामीटर पास करते हो, ए और बी, और सी के लिए हम पॉइंटर या रेफरेंस रिटर्न करा देते हैं। हम हमेशा इस तरह काम करते हैं, राइट? बट when you talk about GPU, you're not going to return anything, but you are going to pass three parameter A, B and C, where C is the result। हम ऐड करा के C में रिजल्ट राइट करवाते हैं। अगर आपको 5 स्टेप्स याद हो तो हमने कहा था कि रिजल्ट को हम कॉपी बैक कराते हैं ऑन CPU। तो वो जो C है सिर्फ वो कॉपी बैक होगा। इनिशियली हम A और B को कॉपी कराते हैं, कर्नल को इन्वोक करते हैं, वो C में रिजल्ट राइट करते हैं और फिर हम C को कॉपी बैक कराते हैं ऑन होस्ट। अगेन हु इज रिस्पॉन्सिबल फॉर रीयूनाइटिंग? हर थ्रेड क्या करेगा, अपनी गिवन लोकेशन पे सम या स्क्वायर करके रिजल्ट राइट करता जाएगा। उसके बाद जो GPU का कंट्रोलिंग पार्ट है वो, या मॉनिटर कह लो, वो क्या करेगा, दैट इज गोइंग टू कॉपी दैट एरे बैक ऑन द CPU। ठीक है, आई होप दिस इज क्लियर। हाउ आफ्टर डिवाइडिंग ऑफ ब्लॉक्स एंड रीयूनाइटिंग ऑफ ब्लॉक्स वर्क? रीयूनाइटिंग नहीं होती, ठीक है, और ये हमारे हाथ में भी नहीं होता। कुछ चीजें ऐसी हैं जो GPU पे जाती हैं तो टोटली आपके हार्डवेयर पे कंट्रोल पे चली जाती हैं। हमने सिर्फ इतना बताना होता है कि हमें कितने ब्लॉक्स बनाने हैं और कितने थ्रेड्स चाहिए, यानी कितने ग्रुप ऑफ स्टूडेंट्स हमें चाहिए, बस। बाकी सारा काम हार्डवेयर जो है आपका, जो GPU है, वो खुद ही मैनेज कर रहा होता है। ठीक है, if I use this example and normal loop, then how quickly this works in term of time? Again, this depends on your problem. First of all, if you can see that कि GPU पे हमें लूप की जरूरत नहीं पड़ी, आपने देखा होगा 32 टाइम्स कुछ काम कराना था। अगर आप इसी चीज को, printf को, अगर आप सिंपली एक सिंपल होस्ट के कोड में लिखते तो आप एक फंक्शन बनाते, my kernel, suppose that is a my host, suppose for का लूप 32 टाइम्स चलता और क्या होता कि वो कोड चल जाता। why for का लूप? because only one thread is involved, for example, yeah, sorry, one core is involved, right? And that one core is going to do that task repeatedly, right? I hope this is making sense now. Example मैंने टीचर की दी थी आपको शुरू में, वो टीचर रिपीटेडली पूरे 1000 एलिमेंट को ऊपर एक ही इंस्ट्रक्शन लगाई जा रही है स्क्वायर की, 1 एलिमेंट, 2 एलिमेंट, 3 एलिमेंट, दैट इज अ फॉर लूप, राइट? फॉर लूप का मकसद भी यही है, टू डू अ टास्क डिजायर्ड नंबर ऑफ टाइम्स। हम यही करते हैं, व्हेन द नंबर ऑफ एग्जीक्यूशन इज नोन, कितनी बार एग्जीक्यूट करना है, तो हम फॉर लूप यूज करते हैं। तो फॉर लूप का काम यही है। बट व्हेन यू आर टॉकिंग अबाउट CUDA, आपके पास एक बंदा नहीं है, बहुत सारे बंदे हैं, बहुत सारे कोर हैं आपके पास काम करने के लिए। आपने सिर्फ इतना बताना है कितने लोग चाहिए, किस फॉर्म में चाहिए। इन अ फॉर्म मींस ग्रुप, आपका काम हो जाएगा। तो देयर इज नो पॉइंट इन लूप, बिकॉज एक बंदे को, एक कोर को एक ही दफा काम करना पड़ेगा, उसमें रेपिटेशन की नौबत ही नहीं आएगी। ठीक है, सो इट वर्क्स लाइक दिस। एक थ्रेड के ऊपर जब एक ही इंस्ट्रक्शन चल रही है, फॉर द टाइम बिंग हम इसको इसी तरह समझ रहे हैं कि देयर इज नो नीड ऑफ फॉर लूप, बिकॉज यू हैव नंबर ऑफ कोर्स देयर हु आर गोइंग टू डू द टास्क फॉर यू। तो एट अ टाइम उसके पास एक ही दफा इंस्ट्रक्शन होगी, और 32 लोग कर रहे हैं तो वो 32 टाइम्स प्रिंट हो जाएगा, राइट? कैन ब्लॉक्स बी मोर देन थ्रेड्स? नो नो नो, नंबर ऑफ, अब आप खुद इस एग्जांपल का आंसर देखें कि हमारे पास क्या नंबर ऑफ ग्रुप ज्यादा हो सकते हैं नंबर ऑफ थ्रेड से? हमारे पास क्लास में टोटल वर्कर या टोटल स्टूडेंट्स या टोटल कोर कितने थे? 50, राइट? अब आपने 50 को ग्रुप में बनाया, 10 के ग्रुप में, और हर ग्रुप में 5-5 स्टूडेंट्स रख दिए, तो टोटल ऑफ कोर या थ्रेड या स्टूडेंट्स क्या रहे? वो हमारे पास 50 ही रहे। ठीक है, तो दिस कैन नेवर हैपन कि हम ये कहें कि कैन ब्लॉक्स बी मोर देन थ्रेड्स। नहीं, ऐसा नहीं होता। ब्लॉक इज जस्ट एन organizing your core into a group, right? Your workers into a group. So I guess these were the all questions I answered, and I guess over to the host now.
Thank you very much, ma'am. ये बहुत ही informative session रहा था. Now we would like to present something for you. So, ma'am, आप अपनी slide share करना बंद कर सकती हैं?
Sure, sure.
Okay, host, please share the screen. This is a very simple thank you from our part, a very small token of appreciation for your time and your efforts. We were extremely glad to have you with us here and learn about something so important and advanced. It is truly an honor to have you with us here. Thank you very much, ma'am.
Most welcome, guys. Most welcome.
And we hope कि जो है ना फ्यूचर में हम लोग आपने जैसे वर्कशॉप वगैरह का जिक्र किया था, so we would love to have that as well.
Sure, sure, sure. Why not? I would happy to share my knowledge with you all.
Thank you very much, ma'am. Okay, now we would also like to thank all our participants for joining us today. I'm sorry that we cannot have audio questions at the moment. If you have any questions, you can forward them to the email which Ma'am Raazia shared with us. Thank you very much for being with us. As I mentioned before, there will be a quiz at the end. The link will be shared to you over email. You will have 24 hours to attempt the quiz, and within 1 week, you will receive the certificate if you score more than 60%. So best of luck, and we hope to see you in more such events. Thank you very much. Allah Hafiz for now.
Thank you, ma'am.
Welcome, welcome.
Allah Hafiz.
Allah Hafiz.